Welcome back. So as I mentioned last time, we're going to talk about galaxies, not just our own, but other types of galaxies as well. And the big thing that I want you to get out of this lecture is how to classify the galaxies. Is it a spiral? Is it an elliptical? Is it an irregular? Those are the three main types. Then each one of those three types, well, okay, the first two have subtypes that they can be categorized according to. And I'll give you some practice towards the end so that you can see what works with that. All right, let's get started. So as always, pause the video until you've got your class notes out. This is going to be Tool 25, looks like this. Got some nice pictures of galaxies on there. So pause the video until you've got that ready to go. All right. So you are here. Okay, most of us are here. Some of us sometimes I wonder, but for the most part, we're all right here. And this is an artist's conception of our Milky Way, because remember, we don't know what the Milky Way actually looks like because we will never be able to travel far enough out that we can actually take a picture of it. But this was done by a space artist. Now, a space artist is an astronomer who, unlike me, can actually draw. So they've taken the actual science, everything is where it should be based on the distances that we know. We also see that we've got our bulge here, we've got our spiral arms, and then you can't really see it in this picture, but then there would be the halo objects out there as well. But we're here about halfway from the center of the galaxy out to the outer edge in the spiral arm here. The Orion arm is the name of our particular spiral arm. Now, the closest major galaxy to us is the Andromeda Galaxy. You've probably heard of it. And it is part of our local group. We are gravitationally bound, so we're all orbiting. There's maybe 15, 20 major galaxies that are all orbiting each other. And then each one of these galaxies has satellite galaxies. The Andromeda has some that are orbiting it. We have some that are orbiting us as well. Now, Andromeda is really hard to see with your naked eye, but you can make out the center of the bulge with your naked eye. This is the farthest object that you can see without using a telescope. But even then, you're going to need absolutely dark skies and absolutely perfect vision to be able to see it. You're not going to be able to see this structure here, even through, a smaller medium-sized telescope. So what they've done here is they've taken a picture through the telescope, through just a regular camera, but they've taken a long exposure picture, kind of like we did for the Milky Way picture before. Now, obviously, taking a picture that long, something like the moon would be so bright, it would just look like the sun shining there. So this is a composite of two different pictures. A quick one that they took of the moon and the surrounding landscape, and the long duration one that they took of the Andromeda Galaxy. However, the size and position are correct. So if your eyes were sensitive enough to actually be able to see the Andromeda Galaxy, this is what it would look like. And it's huge. 100 billion stars. Again, we think this is basically what our own galaxy would look like. But I want you to start thinking in 3D. We're looking out into space, not only out from the local stars, but out of our galaxy itself. There's basically empty, nothing out there space. And then we come to the Andromeda Galaxy. Now, you've probably heard that the Andromeda Galaxy is coming towards us. So this is where it is relative to the Milky Way. So this is the plane of the Milky Way here, and so it's just a little bit below the plane here. We're tilted. Not only is Earth tilted, but our solar system is actually also tilted relative to the plane of the galaxy, and that's why it goes this way instead of just being nice and flat to us. But this is what it looks like today. This is what it's going to look like in a little less than 4 billion years. So it is moving towards us. It is going to collide with us. This is not going to be a major traumatic event, however. Galaxies collide all the time, but remember, galaxies are not things. They're collections of stars. And so when they pass through each other, when these galaxies pass through each other, almost no stars will actually hit each other. The space between the stars is really big. However, think about Kepler's second law. When they're at the closest approach, what happens to their velocity? The velocity goes way up, and so you'll get stars that will end up getting kicked out of the galaxy. Well, let's say the sun gets kicked out. So what? It doesn't make any difference to us. We'll still happily be going around the sun as we go sailing out without a galaxy. We don't need a galaxy for there to be life on Earth. All we need is the sun. So the fact that the sun is in a galaxy or not really isn't going to make any difference. However, this is going to happen. We are going to collide, and it's going to be pretty impressive. I'll be around to see it, but I don't think of you guys. Two of the satellite galaxies, the two major satellite galaxies of our own Milky Way, are the Magellanic Clouds. Now, you can only see these in the southern hemisphere. So if you had grown up in Australia, you would learn about them in 3rd, 4th grade, something like that, because you can see them with your naked eye if it's dark enough. But these are satellite galaxies. They are orbiting the Milky Way. Now, they were originally a different kind of galaxy, but the gravity of the Milky Way is actually ripping them apart because the Milky Way is a big bully. But it's got all this, the mass of all the stars in the galaxy are pulling on these, and that's causing it to get torn apart. And so these are what we're going to call irregular galaxies. They don't have any kind of shape to them. We'll show you some close-ups later on. So just to give you kind of a quick tour, these are galaxies that are outside of our own cluster, not M31, but the rest of these here. So there are galaxies everywhere that you look in space. And like I said, until about 100 years ago, we actually thought these were nebulae, cloud areas that were inside our own galaxy. But now I want you to start thinking in 3D. All of these background stars that you see here are actually closer to us than these other galaxies like the double cluster, for example. So you're looking out of those stars and then much, much, much empty space, and then you get to the next galaxy over here. One of the easiest galaxies to find is M81. The reason for that is because you can find the Big Dipper usually fairly easily. These pointer stars point to Polaris. And about 1/3 of the way from the end of the pointer star to Polaris, you look up just a little bit, and that's where M81 is going to be. Now, M81 is going to be hard to see with your naked eye, but with a decent telescope, you can see it without too much trouble. And this is what it looks like. It's a pretty impressive sight. It's a pretty spectacular sight. So if you've got a telescope, you're interested in doing a little star hopping, you can find Polaris, find Dubhe here, and then just go up just a little bit from that line, and pretty soon you'll see something that looks like this. Now this, of course, is a long exposure picture. You'll probably, through a telescope, with your own eye, you're only going to see kind of a fuzz. But you connect a camera to that same telescope, and now you can start to get some of the really incredible pictures. And you guys know you need an equatorial mount if you're going to do some astrophotography. But hopefully this will kind of tempt you into giving astrophotography a try. Imagine putting that up on your wall and saying, yeah, I did that, right? All right, so the Hubble Space Telescope, getting time on the Hubble Space Telescope is really, really hard. It's expensive to operate. You have to write a proposal just to get, 10 minutes of time on the telescope. And so somebody made a proposal that said, hey, I want to look at empty space. And they're like, what? But they said, no, I do. I want to take a long exposure picture of empty space. And here's the Big Dipper again. Here's those pointer stars. And so Polaris in this case is down here. Remember, everything rotates. So looking at this area right here, there are actually very, very few stars. So this is a blow up of this area. And then this that you see here is this. So there's absolutely no stars in this field of view, the best we can tell. So everything that you see here, every little dot, every little colored point that you see here is a galaxy. We are looking out way, way, way out in space, seeing some of the, up this point, the faintest and therefore furthest objects that we had ever seen before. So this worked so well that Hubble decided to go one better and take the ultra deep field. At this point now, you're starting to look towards the edge of the universe. These are galaxies that were created not too long after the universe was born. So it's just taken that many billions of years for their light to reach us. So remember, when we look out in space, you're looking back in time. You're seeing what it looked like billions of years ago. So when we look at this then, we see all these different kinds of galaxies. So let's zoom in on a few of these. So this one here, this is a spiral galaxy. This is what we've been talking about. And you see that it's got that spiral structure. It's got the bulge and the spiral arms and the disk, and you can even see some of the stars from the halo there. Elliptical galaxies, these are the ones I talked about at the end of the last lecture. They're anywhere from spherical to football shaped from here. Now keep in mind, a galaxy is not a thing. It's a collection of stars. So it looks round only because that's what the orbits of the different stars seem to be. And they're not orbiting anything, they're orbiting each other. All of the stars in the galaxy are orbiting each other. It is not a solid object. And it looks solid because, like we said, this particular star is orbiting here, but there's another one over here that's orbiting, and there's one in between that's orbiting. And so all of the spaces get filled in, and that's what's making it look solid, but it's actually not. Then the third type, this is an irregular galaxy. This is like the Magellanic Clouds. This is a galaxy that's been ripped apart. And you can see that there's basically no structure to this whatsoever. It doesn't have this nice either football shape or the spiral shape that we have here. And these can come in all different types because literally they're galaxies that have been destroyed. So when Edwin Hubble first started looking at these, not the telescope, the man, he started classifying them using what is often called the tuning fork diagram, because it looks, if you've ever seen an old tuning fork that you bang and it vibrates and produces a tone. So the elliptical galaxies then, he classified from E0 to, technically it goes to about E7, you don't see that here, but E0 are the perfect spheres, they're perfectly round, and then they get more and more flattened as the number goes up. These are spiral galaxies, which he classified into three types, an SA, an SB, and an SC. And he classified them based on how tightly wound the spiral arms are. So you see that an SA, they're wound very, very tightly, whereas with an SC, they're wound very loosely, and then an SB, of course, is somewhere in between. A better way that you can do is compare the size of the bulge to the overall size of the galaxy. Here you see the bulge is, about over half the size of the galaxy itself. And again, we're not talking about the absolute size, we're talking about the relative size compared to the whole galaxy. Here with this SB, it's, call it half, roughly half the size. With this SC, it's very tiny compared to the rest of the galaxy. But then there are also the same SA, SB, and SC, but they've got a bar in the middle. And so you see that here's the bulge, but then surrounding the bulge, then there is this bar, and the spiral arms kind of come out from that. Other than that, the characteristics are exactly the same. And we've since discovered that our galaxy also has a bar. So we are actually a barred spiral. So spiral galaxies we've already talked about. They've got three different characteristics. They've got the disk, the bulge, and the halo. The halo is reddish. So what does that tell you about the types of stars that are there? Will I have many O-type stars? No, because those O-type stars are really bright. If there were any O-type stars in the halo, then they would be outshining any of the red stars. Some students say, oh, well, then they must be red giants. But remember, red giants don't live for very long. They only live for maybe 100,000 years. And red supergiants live even less, maybe 10,000 years. So most of these are those very ancient M-type stars that were created early in the galaxy's history. There used to be some blue stars in the halo, but they've long since died. And so it's used up all of its gas and dust. Since these clusters are so old, it's used up all the gas and dust, and so star formation has ceased. There's no more star formation, and that's one of the key things we can find. If it looks red, there can't be any star formation going on. The disk, on the other hand, is bluish. What does that tell you? Is there star formation happening? Well, there must be, and the reason for that is because I've got some blue stars there. That's what's making it look blue, and the blue stars only live for 10 million years. So they must be fairly young. There must be active star formation going on. This does not mean that there are no old stars. There are, in fact, old stars in the disk. There are old M-type stars. There are young M-type stars. But they're getting outshone by the young blue-type stars. And there's no such thing as an old blue-type star because they just don't live very long. The bulge then is yellowish. Yeah, there's only two colors, red and blue. But that's because this has got a fairly even mix of the older stars and the younger and the redder stars as well. The red stars and the blue stars. All right, so let's look at the different classifications. This is an SA. The central bulge is a large percentage of the disk. So you see that here's the whole disk and the central bulge is well more than half of it. And the spiral arms are very tightly wound together. For an SB, the central bulge is maybe half the disk and the spiral arms are more loosely wound. But remember that we can only see the winding of the arms if I happen to be lucky enough to be looking at the spiral face on. I can look at the size of the bulge all the time, no matter which way the galaxy is oriented. That's why that bulge is usually a little more useful than the spiral arms. So here's a type C, and you can see that the central bulge is going to be less than half of the disk. So the central bulge is actually fairly small when you consider it goes from here all the way to here. The spiral arms are also quite loosely wound, as you see with this big one, for example, coming out here and this one here. So the differences are kind of subtle, but if you compare the A to the C, you can see a big difference, and then the B is going to be somewhere in between. And like I said, usually looking at the size of the bulge is going to be your best bet, and then use the spiral arm winding to give you a clue for the rest of it. Now, we also mentioned that there are barred spirals. The classifications A, B, and C are exactly the same criteria. It's just we put this capital letter B to indicate that it's got a bar. So here, the bulge is a large percentage of the disk, and in fact, it also has that bar. So this is an SBA. Here, it's around half, and it's a little hard to see, but the galaxy actually goes from here all the way up to here. And so it still has that bulge with the bar. And then for the type C, now you can start to see that they are actually very loosely wound, and the bulge itself is actually very small compared to the size of the galaxy, which extends from here all the way up to here. In general, I want you to be able to recognize that it's a spiral. If you can get the subtype, so much the better. If you can get that it's a barred spiral, so much the better. But make sure that you can recognize a spiral galaxy. Elliptical galaxies are pretty easy to recognize. If it's a perfect sphere, or as close to it as it's going to get, then that's an E0. E2 is stretched out a little longer. This is just the center part. The actual galaxy is this whole part right here. And again, these are just stars that are orbiting. And then the E6 is starting to get extremely elongated from here. Notice that all these are reddish. Yeah, okay, I know they're kind of yellow-orange. But that's telling us that these elliptical galaxies are actually much older than some of the spiral galaxies because there's no active star formation going on. They've used up all of their gas and dust. And then the last one we want to talk about was the irregular galaxy. Notice that it's blue. The blue tells us there is active star formation going on. In fact, it's very vigorous star formation because it's like everywhere. Well, that's because this is generally is two galaxies that have collided. And so you've got this compression of all the gas and dust. And so all of a sudden I get this wave of star formation forming through here. So there are no subtypes for an irregular galaxy because they can be pretty much any shape. All right, let's get some practice. So mainly I'm interested, can you identify, is it a spiral, an elliptical, or an irregular? And if you can get the subclass, fine. But the main thing I'm looking for is that spiral, elliptical, or irregular. So first of all, what is this? Spiral, elliptical, or irregular? That one's going to be a spiral. Now, let's try this. Is it an AB, an SA, SB, or SC? So look at the bulge compared to the rest of the arms. And yeah, that's going to be a C because the bulge is really tiny compared to the whole size of the galaxy itself. How about this one? Spiral, elliptical, or irregular? That one's going to be elliptical as well. And this is an E2. It's basically about as stretched as the comparison one that you saw before. How about this one? Well, bonus points if you said it is a barred spiral because it actually is. It is a spiral. And the bulge is small compared to these loosely wound arms. So this is an SBC. How about this one? Looks like a paw print. That one's going to be an irregular galaxy. And of course, irregular galaxies don't have any kind of subtypes. How about this one? Spiral, elliptical, or irregular? That one's going to be an elliptical. What would you guess for the subtype? Yeah, it's almost perfect sphere, so it's going to be E0, maybe an E1 at the best. How about this one? Well, now we're looking at it edge on, but it is still a spiral. So even though I don't see the spiral arms there, I can see the bulge, I can see the disk. So that tells me it's definitely a spiral. Here's the size of the bulge compared to the size of the disk. What do you think? That one's an SB. You see, it's about half the size. And, you know, if you figure it's between an SA and an SC, well, the only one that's there is going to be an SB. All right, so make sure that you've got your Galaxies practice sheet. We're going to ask you some questions, some interpretation questions. So I'll give you a hint on this. Think about what you know about the colors of stars related to star formation, how old they are, how young they are, things like that, okay? So think very carefully about this. And also remember, I'll give you another hint. If I have red stars, are all red stars old? Think about that, okay? Okay, so now you know the three different types of galaxies that are out there, the spirals, the ellipticals, and the irregulars. The Hubble originally thought that the ellipticals evolved into spirals. Think about that. Is that possible? Which of those two has the older stars? Well, the elliptical has used up all its gas and dust, so it must be the older type of galaxy as opposed to the spiral galaxy, which still has star formation going on. So Hubble got it backwards, and here's one of the greatest names in astronomy, and he just was completely wrong. There's absolutely no way that that elliptical galaxy could evolve into a spiral. We still don't completely understand where the different types come from and why some are elliptical and some are spiral. We're starting to get there. And so, if you ever take an upper level astronomy class, we'll spend more time on galaxies with that. That's all for this time, though. So if you have any questions, though, make sure you come by Live Help. Make sure you're getting the help that you need. That's what I'm here for. We'll see you next time.